Hey, so good afternoon everybody and welcome to the machine learning course. Today I'm going to split these 2-hour sessions in 2 blocks of 1 hour. So we'll have a short break, and this first part before the break I'm going to talk about some formalities on the course, how the lectures will go on, the tutorial classes and so forth. And then we'll start looking at some basic concepts for machine learning. What machine learning is, what it's good for, and what we want to achieve in this course. So what are the goals and more or less the roadmap for this course. Then on the second hour today, I'm going to talk a bit more in detail on the first concepts that we'll start to use in machine learning. So to start, my name is Ludwig. I'm going to give the lectures and the first tutorial slot, which is currently it's reserved for the Big Data Masters program, but there will probably be some vacancies left, and afterwards we'll open it to everyone. There are currently another 4 slots for tutorials, but we're going to open one 6th tutorial slot. I don't know exactly when it will be. It will probably be on Thursday's morning, but you'll see it appear in clips. So currently these tutorials are overbooked and a bit crowded, but after the other one appears you can check to see if it's more convenient for you, and you can unenroll yourself from your current tutorial and try for another one. Or you can switch between the tutorial classes among yourself. Clips allows you to do that. So the course site, this is probably the only thing you need to write down for now. You'll have the slides there, and if everything goes well, you'll have the recording of the lecture. There's also some notes for the lectures and other material. It will appear there. So my intention is to, for these lectures, I will split them into 2 1-hour blocks, and in general I will try to cover about 3/4 of an hour with my talking, and then leave always some minutes for discussion and for you to ask questions and so on. So this should help you keep up with the subject and keep clearing up any questions you have along the way. The tutorials. Most of them, there are some tutorial classes reserved for the assignments. When the assignments come, we'll talk about that. But most of them are exercises, and especially in the first one, you have quite some detailed guidelines for the exercise. So it's possible, and I would recommend it, that you try to do part of the exercises at home, and then use the tutorial class to try to ask questions and to help with any exercise that you couldn't do. But in theory, you should be able to start them at home, at least the first one. All of these, the exercises, the PDF file with the exercises is also, you can also find it on the course site. For the assessment, there are 2 components: a theoretical component, which is the test or the exam, and the practical component, which consists of 2 assignments. The assignments can be should be made in groups of 2 students, and you have until the 7th of October to decide on the group. I will then later tell you how to register the groups, but you'll do everything by email, by sending an email to this address, but I will post it on the course site when the time is right. So you can take these first tutorial sessions to get to know each other, and then decide on the group. The tutorial classes start next week. So today we only have the lecture, not the tutorial. There are no tutorial classes this week. They start only next week. For each of these components, theoretical and the practical, you need to have a passing grade. So you need at least 9.5 on each of them to pass. 2 important notes. For the exam, so if you have 2 tests, if you fail the theoretical part on the test, you can take the exam after the classes end, and the exam is scored in 2 independent parts. So for each part, you are guaranteed the grade you had on the corresponding test. So if you have a very good test, you don't need to answer the exam for that part. You can focus on the rest, or you can answer everything to improve the grade. So, but in any case, for the exam, you still carry the grade for the test and can use them. Another important point is that this address that you'll use for registering the groups and for handing in the assignments is only used for automated processing. So if you have questions, you contact the teacher for your tutorial, or if you have questions about the theoretical part, you can contact me, but don't use that address for questions, because that is only for submitting that information that will be processed automatically. If you have completed the practical, so if you've got a passing grade on the practical component in the last 3 years, you should not enroll in the tutorial classes if you want to keep that previous grade. So if you have enrolled already and are in these conditions, please remove yourself from the tutorial class. We're going to use Python 3.6, and we're going to use several libraries like scikit-learn, matplotlib, and so on. So the best thing, if you want to install the same software that we are using in the lab, you can install this distribution of Python Anaconda, which includes all the libraries that we need. So just go to that site, download and install, and you have the same integrated development environment and all the libraries that you're going to use. The main bibliography, so the main references for you to study should be the lecture slides and lecture notes. There is a PDF file on the course site, and the main book is this one by Bishop, Pattern Recognition. So this would be the book I'm going to refer to more often. There are 3 other books here, and I'm going to refer to them also occasionally, but the idea is not that you need to read all 4 books. The purpose of this is that, at least for the theoretical part, also partially in the practical assignment, this course focuses a lot on understanding the concepts. And sometimes when you see something explained in one specific way, it may not be as clear as it becomes if you see it explained in different ways. So the idea of having different books is not that you're going to read everything, but that you can always look up the same thing written in a different way by a different author, and that may help understand the concept. Okay? So the main idea here, we're going to talk about machine learning, and it's good to have a notion of what the subject is. And as you can see from this quote from 1959, this is not a new concept, although currently it's much en vogue, the machine learning thing. The idea is quite old, and the main idea is that we can create some system in the computer that will learn from experience. This is the basic notion of machine learning. You have a more formal definition by Mitchell more recently, in that we have this experience, this E, which is some information our system is receiving. We have some tasks or a set of tasks, and we have a measure of the performance in those tasks. And we say that the system is learning if, as we feed it the experience, if we feed it the data, that performance in those tasks improves. And this is a more formal notion of machine learning. So basically, we are looking at these elements, the tasks that we want to do, the measure of the performance, and the data, the experience that we are giving. And if the performance is improving, then the system is learning. So if we can identify these 3, then at least we can define our machine learning problem. Note that this may be a bit different from what we sometimes talk about learning when we talk about dogs or children or something like that, because we are not worried about trying to specify what is exactly the experience we're using, what the task is, and how to measure the performance. But when we're talking about machine learning, if we want to build a system that learns, we need to define these things in some concrete terms, because otherwise we cannot really tell if it's learning or not, or we cannot specify the problem concretely. So let's see just an example to illustrate. We have this task, which is to identify requests for information or booking tickets in flights. So a person calls on the telephone, the system answers and tries to identify and determine what the person is trying to do. If she is asking information about arrival time, or she is booking a ticket or something like that. So we need, this is the task specified, we need a performance measure, and we can compute how many correctly identified parts of this conversation our system is able to do, or how many errors it commits. It turns out to be equivalent. We have the data to feed into our system, that is the experience our system needs, and these are the annotated records. This is the reference for the paper, and it's something like this. So we feed into the system records that look like this. So we have a voice processing module first that converts it into text, for example, and then we feed in the text, and the system, when it's working, should output something like this. So please book me on. This is a request for booking a flight. Flight 21, this is the specification of the number of the flight, and so on. So the system should be able to receive those messages in text or in voice, which is then converted to text, and label correctly the different parts. The experience that we are giving the system, so it can learn first, is similar to that which we want to obtain when the system has learned. So first, we give it a set of labeled messages like this. We force the system to identify everything correctly by comparing with the labels that we have, and then we can measure the performance. So this is one example of one way of teaching the system to perform in some manner. And we have different types of problems that we can think of for using machine learning. These are just some examples of different classes of problems. Regression problems are those in which we try to predict the value of a continuous variable. For instance, we want to predict prices for stock or for houses or things like that, given some information. We have classification problems in which we want to partition our data points into different categories, into different bins, for example. So this could be classification of emails to divide them into spam and non-spam. And then we have other kinds of problems. We want to find out, for example, if people who buy potato chips also buy beer, so we want to put them strategically placed in our supermarket to improve purchases or things like that. Or we want to do other types of learning in which we are not really trying to predict something, but we are trying to change the way the data is presented, or the kind of information we can get from the data. And we can use clustering, for example, if we want to group together things that are similar and deal with groups instead of individual examples, or try to find the shape of some distribution given some examples, and so on. So there are many different types of machine learning problems, and they are not restricted to trying to predict something or trying to classify something. And we'll see along the course, we'll focus on some of these types. Machine learning is also related to several different disciplines. Computer science, of course, because we need to implement the systems that are learning, so we need to be able to put the computer to work on these algorithms. But there will be a lot of statistics and probability. You can think of machine learning, actually perhaps a good way of thinking about this is that machine learning is that subset of statistics and probability theory that you can actually use in practice with computers. So if you add the restriction that we must be able to have the computer compute the solution to the problem, this is basically what machine learning is like. So the drawback of this, the disadvantage for for many of you is that you're going to see a lot of equations about statistics and so on in this course, because that is the grounding for many of the algorithms we're using here. What makes this very different from a statistics course is that our goal is not merely to look at the statistics, but then to implement something that will automatically find the correct parameters, adjust the model, and learn what we wanted to learn. So that is the part that makes machine learning different from statistics. Of course, mathematics, we not only need the statistics part, but then we need all the numerical tricks and mathematical for being able to solve the equations. We are not going to focus on that part here, so we are not going to talk about the optimization algorithms that run behind the interface that you're using to use these algorithms, but we must pay some attention to them because they impose some limitations on what we can do. We can have a very nice model to try to learn something, but then if we don't have a good numerical algorithm that can find the parameters, then we cannot use the model because we cannot do anything with it. There are relations to other things outside mathematics and computer science. For instance, a lot of modern machine learning algorithms like neural networks have some inspiration on neuroscience, and also there are problems that arise and relations to philosophy, both in what we really mean by learning and knowing something. We are looking here at a more operational aspect of learning and knowing, which is according to that measure of performance. And this is different from what we usually think about when we say that we learn something. Learning something in another sense is not merely improving performance, but we really must understand things and so on. When we talk about machine learning, it's a different sense there. And also it raises some important ethical problems, because if you have a computer program that controls, say, an electrical grid or something like that, and there is a fault and someone dies, you know that that was an error in the program. Somebody wrote the program, and maybe you can find if they are at fault or if it's something that was unpredictable. But if you have the same thing controlled by a machine learning algorithm that learns from data and then does some error, it's much harder to figure out who is to blame, what's wrong there. And when you start having cars that drive on their own and lots of other things that can happen, then it's the ethical problems here raised are if we shall or if it's legitimate for us to get rid of that responsibility for the consequences of the systems that we create, or even if they are autonomous, we are still responsible for what happens. So we're not going to cover those things, but at least to give you an idea that as this field develops, it's probably going to raise some important questions here. So what can we use machine learning for? What's the point of doing this? Basically, whenever you have a problem that you do not know explicitly how to solve, if you want to solve it with a computer, you should use machine learning. That's about the set of problems where machine learning is very useful. So if you know exactly what is the algorithm for solving some problem, you just implement the algorithm. But consider, for example, that you want to identify handwritten digits. There may be an algorithm that you can write that identifies handwritten digits. So if it starts with a black corner and then there is a line or something like that. But if you want to try this for all these kinds of handwritten digits, then this would be a very complicated algorithm, and probably no one can really write an algorithm to identify handwritten digits. So what we can do is to take a sample of handwritten digits, convert or find the corresponding digits in some representation that the computer can use. So we actually type in everything. We have some people recognizing these and labeling them correctly. And now we have a training set, a set of data that has the correct labels that we can use to adjust our models and evaluate the performance in identifying these digits. So now we find a function, we have a lot of parameters, we optimize those parameters, and we find a way for our generic algorithm finds those parameters so that the computer then can do the translation between the image of the handwritten digits and the actual digits. We don't know what the algorithm is. We just have this statistical model that usually when there is a pixel there like that and a pixel there in the other value, then it's this number or that number and so forth. So what is this useful for? Basically, when there are many situations where, because the problem is very complex, because there is a lot of data, because the problem changes rapidly, it's not feasible to think about, for humans, to think about the algorithm and to implement the algorithm in each case. So we can have large volumes of data. For instance, if you want to find a way of correlating or relating the string for a Google search and the right web pages, if you try to do this manually by figuring out rules corresponding each one query to these pages, then you have so many queries and so many pages that you don't have enough computer scientists to implement such an algorithm. So this is an example where you can take all this data and use machine learning algorithms to find the right relation. Or if you're looking at Facebook data or credit card fraud and so on, when you have huge amounts of data, not only it's hard for humans to process so much data, but for machine learning, the more data you have in general, the better, the easier it is to train your algorithm. Also, when you need systems to be adaptive, because it's suddenly, so suppose that you have a credit fraud of some kind, you start detecting it, you implement some measures to prevent people from committing that fraud, and now they start doing it in a different way. So when things change rapidly, it's very difficult for you to reprogram all your algorithms to respond to these changes. But if you have a system that can be retrained automatically, then you can retrain it and keep adapting it to the changes. Also, when you need to, in the limit, have many different algorithms. For example, when you see the Facebook feed, it's customized to what you usually like and what you usually click on, and so for each person the feed is determined in a different way. If you need to have a computer scientist look at the pattern of usage for each person and customize the feed, this will not be feasible. But if you have a system that learns, then the system can create a different hypothesis, a different way of figuring out, of sorting the news that you find for each different individual, for each different user. So all we need is a set of parameters that varies from user to user. So in general, machine learning is good when you don't have a recipe, or either because you don't have time to come up with a recipe, the algorithm, or the problem is too complex, and you have enough data to train the system. Because we need that component, the experience part, the data, so that our model can learn, our system can learn. And if we don't have that data, we cannot use machine learning. So when these two conditions are met, and at present they are met increasingly often because we have all these social networks and all the information that is constantly gathered on everything. So we have lots of data and we have lots of complex and quickly changing conditions. So now let's cover some basic concepts that we'll use to structure the course and also to think about these problems. First is the hypothesis path, which is a set of hypotheses from which we're going to choose the way to solve our problem. So we're going to choose one hypothesis. And basically the process of learning is the process of finding the best hypothesis from this set. Now we need to assume something about this set of hypotheses before we start learning. I'm going to give some toy examples to make it easier to understand what we're talking about here. Suppose that we have these data, these red and blue dots, and we want a system that learns to separate the data. So our set of hypotheses of ways of separating the data could be, for example, horizontal lines. We have the set of all horizontal lines, could be different ways of separating the data. We could separate the data here, so red above, blue below. We could separate it here, anywhere. And the system will learn by improving the performance in separating these sets and choosing the best of these hypotheses. Now, we also have this model, which is a representation of the set of hypotheses. Typically, we can represent our set of hypotheses with an equation and some parameters. In this case, we can represent horizontal lines by this equation, epsilon less or equal to theta. This would be the blue class. The red class would be on the other side. And this theta 1 here is the parameter that we can change to scan all our hypothesis class. So these are the first two concepts. The hypothesis class is the actual set of hypotheses. The model is one way of representing that set of hypotheses, generally with parameters, and we adjust those parameters to try to find the best hypothesis. So you can see that if theta is too low, then we are not cutting this at the right place. If it's too high, it's also wrong. But if we put it somewhere here, we can separate the two sets well without error. So this would be the learning process to find that value. But we can have other hypothesis class represented by other models. For example, suppose that we are going to consider circles of radius 1. Now we have two parameters. The radius is fixed. The blue class is always inside the circle, but we have two parameters because we can decide on the x and y coordinates of the circle. So now we have a different set of hypotheses, all the circles of radius 1, and we have a different model in which we represent all these circles by the parameters that we can change. So basically the hypothesis class is the set of all hypotheses from which we are going to choose. The model represents this set of hypotheses, generally with parameters that we can then adjust to try to find the correct hypothesis. The hypothesis is one specific element of the hypothesis class, or in general, one instance of the model that we obtain by fixing all the parameters. If we assign values to all the parameters, then this is a single hypothesis. A single line, for example, epsilon less or equal to 0, this is one hypothesis from the first hypothesis class. This would be a circle with centers at minus 1x, minus 1y, would be another hypothesis. So our goal when we're learning is to find the best hypothesis. The trick now, remember, we need this performance measure, so the best one is the one that gives us the best performance, but we need to define this performance measure in order to find the best. There is also another issue here, an important point, which is this inductive bias, which is the bias that we introduce by fixing the hypothesis class. So if, for example, we decide that our hypothesis class is the set of horizontal lines, we will never find a diagonal line here to separate the two, because that is not included in our hypothesis class. We're going to see this a bit more formally later on the second half of this course, but we always need this inductive bias. We need to restrict the set of hypotheses, because if we allow any hypothesis, we lose the ability to extrapolate from a set of known data to the unknown data that we're going to try to use our problem on again. So we're going to look at this more formally later on, but you can ask, for example, let's not assume that gravity will still be working tomorrow. So if you don't assume that, then you cannot make any arrangements for dinner, for something, or because if gravity suddenly stops working, then everything blows away. And you need that assumption in order to do some extrapolation for what will happen tomorrow. In general, if you want to infer outside the set of data that you have, you need to assume that some things will still remain constant, or there are some limitations to what can happen outside. So, in these cases, we can only extrapolate from this set of data to other new points that come later if we assume something that remains constant between the different stages or the different data that we're going to get. For example, if we assume that the sets are always separated by an horizontal line, or if we assume that the blue set is always within a circle, or something like that, then we can train with one set of data and predict outside. If we don't do that, then we cannot do any extrapolation. So let's see some different kinds of problems in machine learning that we're going to cover here. First, a simple kind of problem is the unsupervised learning, which occurs, you don't see very well, there should be an error here. We have some features, we can describe our data with some feature values, for example, the coordinates of points, or color, height, weight, something like that, a set of features that describe each of our examples. And we want our system to learn a way to provide us with new feature values. This happens, for example, when we're clustering. The new feature values would be the labels of the cluster. These sets of points belong all to the cluster A, these points belong to cluster B, and so on. We are not doing this in a supervised manner because we are not actually beforehand, we don't know which cluster they will belong to, but we can assess the results, for example, in this case, by clustering images. So this program here, this paper, describes clustering images based not only on the image itself, but also on labels that the HTML page can have assigned to the image. So we have here different groups of images. You see that there are images that have similar look, similar colors, and so on. There are images that have somewhat similar colors, but you see here Pluto, and you see here Pluto too, so the label is the same, and they get grouped together. And what we have here is that we start with a set of images, and then we obtain new features, let's say, that correspond to which group each image belongs to. So we are creating new information about these images. This contrasts with supervised learning. So in unsupervised learning, we take the feature values, we learn something, and we show the new features. For example, the clusters the examples belong to. In supervised learning, we have the data, and we split it into two parts: the values that we want to predict, and the values of the features. The feature values will go into our learner, and the learner will try to predict the target value. And since we know the target value, because the data is labeled, already has the target value, then we can measure the error between the two. We can see how far away our learner is from the target, and this allows us to supervise the learning progress and force our learner to predict as well as possible the target value. So in supervised learning, what we are feeding into the learner is a set of features. We get from the learner a prediction that we compare in our training data with the labels that we already have. So we know what it should predict to be right in that data. After it learns, we hope that it will predict correctly the points that come afterwards and for which we do not know the exact value. For example, we can have a regression problem in which this is a continuous value. For example, the price people will pay for an apartment, for renting an apartment. And you can have features like the number of rooms, the floor the apartment is in, the neighborhood it's in, and so on. And if you can use that correctly, you should be able to predict how high you can ask for when you're renting out the apartment. And if that prediction is correct, then you can use that model. To train that model, you can check with some apartments that have been rented and use that data to adjust the prediction. So regression problem will be a supervised learning problem with continuous values as the target value. If the target values are discrete values, are different categories, then we have a classification problem. For example, we have a database of emails. We know that some of them are spam, some of them are not. We feed in the email text, all the emails to our learner, it predicts whether or not it's spam, and we measure the number of errors. And we try to change the parameters in our model until the errors decrease as much as possible. So this is these are two types of supervised learning. This is an example of supervised learning. We have a data set of faces. So these are known examples. We can also include here in this set examples of not faces, and then we feed in all these known examples to our learner, and it learns to identify what is a face and what is not a face, depending on the kind of learning system that we have. And then we can apply it to, say, pictures or photographs, and we can have it try to identify face. This also illustrates here a problem. If you see here, maybe you cannot see it very well, but there is a person here, but the face was not identified. This person has her head is slightly tilted, and all the examples have the head straight, so the system does not know that this is a face. And this is an example where you can have a low error on the training set. It can maybe find all the faces in the training set, but then there is an example that appears different, and the system cannot identify it correctly. But this is an example of supervised learning. Then we have, for our course, we're going to focus on the two first ones, first supervised learning and then unsupervised learning. But there's also a different type of problem, which is reinforcement learning. This is one where you can do some evaluation, but you cannot evaluate all the decisions the system is making. So not all instances can be evaluated. Suppose that you're training a car that drives itself. At each instance, the computer needs to determine how to steer the wheel, how to accelerate, brake, and so on. At some point, it crashes into a tree. But now you need to figure out where was the mistake, because it's not at the instant the car crashed into the tree. It might have been a few seconds before something the system did wrong. So you need lots of these examples and try to assign credit to all the different choices. The same if you want to train a system to play chess or to do something like that, in which you only know if things went well or not when the game ends and you find out who wins. So this is basically, you have the features. They can be all the data from the sensors at each stage, or what is the state of the chessboard for each play, and then the system needs to evaluate the different actions at each stage, but it can receive some feedback when things go wrong or when things go right, when it reaches a goal. So it's different from supervised learning in that you cannot evaluate each of the actions or each of the predictions of the system, but there is some feedback that you can insert into the learning process. So examples for reinforcement learning are robotics, where the robot has to learn to manipulate things, autonomous vehicles, and things that, for example, in game theory or something like that, when you have to use in practice, play some games, and you need to figure out how to win the game. If the game is too complex, so theoretically you could have a set of explicit rules that tell you exactly which move to do in chess depending on the state of the board. So if there is a pawn here and a knight here and so on, you should play this way. If there is something like that, you should play this way. In theory, you could do that. But since chess has so many combinations, you cannot do it in practice. You cannot explicitly state all the rules. You can do that for tic-tac-toe or something like that, but not for chess. So this would be trying to figure out an approximation to that set of rules by reinforcement learning, by trying to assign credit to each move depending on what came out at the end. Then there is another type of machine learning problem or approach, which is semi-supervised learning. This happens when you join together supervised learning with unsupervised learning. So suppose that you have a set of 1,000 images that are labeled, for example, for birds and cats and dogs and so on. And then you have a set of 1 million images that you can gather from the internet, but you don't have these labels. Nobody labeled them with what kind of animal they were. But if you group them together by similarity, then you'll probably find a lot of images that are not labeled, that are similar to some of the images that you have labeled. So if you have an image that you know that it's a dog, and you have lots of images that are very similar to that one, you can probably say, okay, all of these are dogs, and now you can assume that to train your system. So basically the idea for semi-supervised learning is that you use unsupervised learning to get more data for training your system. So our focus here will be on supervised learning for the first part of the course, and then unsupervised learning for the second part of the course. The reason for this is that with these two we can cover the basic concepts, the problems, and understand how things work, and then basically the others are an extension of this, so we don't cover it here. The idea of this course is that it gives you a foundation for machine learning. So these are the goals of the course. You understand why we do things in a particular way in machine learning, what it's for, and these basic concepts. You get some experience with useful machine learning tools and applications. So in particular, we're going to use scikit-learn. Lots of the algorithms we're going to talk about here are implemented there, and you can experiment with them. And then this is perhaps the most painful part. You need to get the basic knowledge to understand the literature, so you can read a paper or a book or something like that and understand the algorithm. So this requires that you also be able to understand the mathematical formulations. And this is the part that is sometimes a bit painful. So I'm going to show you lots of equations during this semester, but the idea is not that you memorize the deductions or the proofs. It's not that you memorize the formula, and you don't need to know it by heart, but you need to learn how to read that notation. Because this is basically the language of machine learning, it's the language of statistics, and if you take a paper or a book or something like that, you need to be able to look at the equations and understand what's there. So this is the goal here. I'm going to give you lots of formula, but it's for you to learn how to read them. So we'll start by this introduction and supervised learning, regression and classification. This is basically the first half of the semester, and it will correspond to the first step. The first step will be for supervised learning with regression and classification. Then we'll start the second part of the semester with learning theory, some more formal approach to some problems that we're going to look at in this first part. And then unsupervised learning, which is mostly clustering and also feature extraction and so on. Okay, to sum up this first part, machine learning, we're going to try to get the computer to learn without us having to tell it explicitly what it's going to do. So for this, we're going to select a hypothesis class, a set of possible ways of doing what we want it to do, and then we're going to get the computer to choose the best hypothesis from there. So we can think of machine learning as selecting the best hypothesis from a class of hypotheses. This leads us to inductive bias. When we select a class of hypotheses, we are deciding that things must always be like that, so always a line or always a circle or something like that, and that cannot change. This is a limitation that is necessary to allow us to extrapolate from one set of data to what comes next. Without this limitation, there is no extrapolation. And we saw here some differences. Supervised learning, we have the target values, and we can check for each prediction if the system, how wrong or how right the system is. And supervised learning, we don't have target values, but we want the system to give us new features. For example, clusters, or which ones are alike, which ones are different, and so forth. Reinforcement learning, we have some feedback, but not for each prediction. We need to do a set of predictions or a set of actions, and then we figure out that things went wrong or things went right, and we need to assign credit to all those individual choices. To me, supervised learning is a mixture of supervised and unsupervised where we can enrich the data. So you have chapter 1 of Alpide, Mitchell, and Marsland cover more or less these ideas if you want to read them, this introduction on these books.